everyone. For today's lesson, we are learning about inverses and square root and cube root functions. Our warm-up for today is to practice solving for x. So I would like you to please solve for x. We have two separate equations. Our first equation is x plus 3 cubed is equal to negative 343. And our second equation is x minus 4 squared is equal to 36. What I would like you to please do is please pause the video, and I would like you to solve each of these. You are welcome to refer back to our first day of notes to help you with solving these equations. When you have an answer, please restart the video and we will see how well you did. Okay, so our first equation is x plus 3 cubed equals negative 343. And we know that in order for us to eliminate a cube, we need to take either the cube root of both sides or raise both sides to the 1/3 power. I am going to take the cube root of both sides, but I do have choice in the matter. The cube and the cube root will cancel away, leaving us with x plus 3. This is equal to, well, I just took an odd root of both sides, and I am taking the odd root of a negative number, which means that I'm going to have a negative answer. And the cube root of negative 343 is negative 7. From here, I'm going to subtract 3 on both sides, and we find that x is equal to negative 10. We end up with only one solution. Let's look at number 2. With number 2, we have x minus 4 squared is equal to 36. To undo a square, I'm going to take the square root of both sides. And when I do that, the square is eliminated by the square root, leaving us with x minus 4. But when I'm taking the square root of both sides, I am taking an even root of both sides, which means that I'm going to need plus or minus in my answer. So x minus 4 will equal plus or minus 6. Remember that whenever we're taking the even root of both sides and we're solving an equation, that's when we need plus or minus. So what this means is it means that we have x, if we were to get x alone, we are going to add 4 to both sides, and we find that x is equal to 4 plus or minus 6. So this means that we have two solutions. Our first solution is 4 plus 6, which is 10, and our second solution is 4 minus 6, which is negative 2. So we end up with two solutions, x equals 10 or x equals negative 2. So our learning targets for today's lesson is for us to be able to say I can recognize the inverse of a quadratic function with a restricted domain as a square root function. I can recognize the inverse of a square root function as a quadratic function with a restricted domain. I can recognize the inverse of a cubic function as a cube root function, and I can recognize the inverse of a cube root function as a cubic function. So we're going to be talking about those relationships between functions that we've already learned about, cubic and quadratic, and how they are going to lend themselves into what we're going to be doing next, which is graphing square root and cube root functions. So let's go ahead and recall what an inverse function is. So an inverse function, obviously functions have to pass the vertical line test, but they have tables where the x and the y values have been switched as ordered pairs. So the ordered pair switched from its original function. And they have graphs that are reflected over the line y is equal to x. So this is what we learned a couple of units ago. And also recall the steps for solving or identifying a inverse function algebraically. That's where we replace f of x with y, we switch x and y, solve for y, and then replace y with f inverse of x. So we're going to be following these steps as well in our first example. So in our first example, we're going to consider the function f of x, and then we're going to create a table for f inverse of x. So f of x has the ordered pairs 2, -2, 3, 0, 4, 0, and 5, 4. And to come up with our inverse table, all we do is switch x and y. So I'm going to write -2, 2, 0, 3, 2, 4, and 4, 5. Letter B is asking us to graph both functions, so that's exactly what I'm going to do, starting with our original function of f of x. So over here, I am going to graph -2, 2, 2, -2, 3, 0, 4, 2, and 5, 4. And if you have a straight edge with you or a piece of paper or something like that, you can go ahead and connect these points to create a straight line. And we can see that this is linear. Let's go ahead and look at our inverse. Our inverse function, we have -2, 2, 0, 3, 2, 4, and 4, 5. And using your straight edge, I would like you to please go ahead and connect these points. And what we see is that both of these graphs are reflections of each other, and they're reflected over that line that we talked about before, which is y is equal to x. So if we were to graph the line y is equal to x, we'd go to 0, 0. Our slope is 1, and what we will see is that these two graphs are indeed reflections of each other across the line y is equal to x. So all I'm doing here is applying the slope, going down one to the right one, or down one to the left one, and coming up with my points. Up one to the right one. So we can see clearly that these two graphs are indeed reflections of each other. So now what we want to do is we want to write the equation of f of x, and it appears that it is crossing through. It has a b value of 6, so I'm going to write that my b value is equal to -6, and my slope appears to be 2. So I can write my equation for f of x as f of x is equal to 2x minus 6. So that is just using my algebra skills that I've learned before. I recognized that this is linear, and a linear equation is in the form of y equals mx plus b. I can clearly see what my b value is. I can see what my slope is, and here's my equation for f of x. To find f inverse of x algebraically, I'm going to start with f of x is equal to 2x minus 6. And I'm going to replace f of x with y equals 2x minus 6. And then I'm going to switch x and y so that it is x equals to y minus 6. And now I'm going to solve for y. So I'm going to bring 6 to the other side by adding 6 to both sides. I end up with x plus 6 is equal to 2y. And then I'm going to divide every single term by 2 so that I end up with 1/2 x plus 3 is equal to y. Now that I know what y is, I can write my inverse function of 1/2 x plus 3 is equal to f inverse of x. And here is my inverse function. And so all of this should have been a recall of what we've done before. This should not be that bad. And what we're going to do is we're going to take this idea of inverses of linears to the next level. And we're now going to talk about quadratics and cubics. Starting with example 1, what we have is we have g of x is equal to x squared minus 4. And we have a restriction on the domain. We have only x is greater than or equal to 0. So this is a restricted domain to only have positive x values. You could restrict the domain to have negative x values if you would like, but this domain has been restricted to only positive x values. So for letter A, we're going to find g inverse of x algebraically. So to find g inverse of x, I'm going to start off with writing g of x is equal to x squared minus 4. I'm going to replace g of x with y, so y equals x squared minus 4. And then I'm going to switch x and y, so I have x is equal to y squared minus 4. And at this step, I need to solve for y. So I'm going to solve for y by adding 4 to both sides, just like we did before. X plus 4 is equal to y squared. Now, the way to get rid of a square is we would take the square root of both sides, just like we did in our warm-up. And this is an even root, so we would end up with plus or minus. However, if we have plus or minus the square root of x plus 4 is equal to y, we have a restriction on our domain. So if we had to pick between the plus or the minus, we only want positive x values. So therefore, we're going to pick one. We're going to use the plus because of the restricted domain. If our domain was restricted to only negative numbers, we would use the minus. So therefore, I can write a plus sign, or I can just keep it. The square root of x plus 4 is equal to y. And so that ends up being my inverse function. And I can rewrite it up here in inverse notation of g inverse of x is equal to the square root of x plus 4. All right, now for letter B, we want to graph both g of x and g inverse of x on the same exact graph below. And we're going to make a table. So when we make our table of values for g of x, we only want to use positive x values as well as 0 because 0 is included. So I'm going to let x equal 0, 1, 2, 3, and 4. And I'm going to substitute 0 in. 0 squared is 0. 0 minus 4 is negative 4. 1 squared is 1. 1 minus 4 is negative 3. 2 squared is 4. 4 minus 4 is 0. 3 squared is 9. 9 minus 4 is 5. 4 squared is 16. 16 minus 4 is 12. Let's go ahead and plot these points. So I have 0, negative 4, 1, negative 3, 2, 0, 3, 5, and 4, 12 I cannot plot. So to the very best of my ability, I'm going to connect these points. And here is my half of a parabola. Now what I'm going to do is I'm going to switch my ordered pairs, and I'm going to identify and graph my inverse. And I'm going to plot negative 4, 0, negative 3, 1, 0, 2, 5, 3, and 12, 4. So I'm going to start with negative 4, 0. Here is negative 3, 1, 0, 2, and 5, 3. I can't plot 12, 4, so I'm just going to make sure that my arrow is pointing in the correct direction. And what we see once again is that these graphs are indeed reflections of each other across the line y is equal to x. So we can clearly see that we did a really good job of graphing and identifying what our inverse is. But what we see is that they are indeed inverses of each other. And this is what we call a square root function. It has a starting point, and then it has an arrow going in one direction. And so that starting point is really, really important. It affects our domain and range. So let's go ahead and talk about the domain and range of our function. So the domain of g of x was our very first graph that we did. That was of our restricted quadratic. In our domain of our restricted quadratic, they gave us x has to be greater than or equal to 0. And whenever we look at domain, we always read it from left to right. And our first x value that we have starts at 0. And then I have technically an arrow going to the right up here, indicating that this is going to continue forever and ever towards infinity. So our domain, it starts at 0 and it goes to infinity. You can also write it as x is greater than or equal to 0, as mentioned in the beginning. Our range, we always read from bottom to top. So we have nothing until we reach this minimum point of -4, and then we have an arrow that's technically pointing up. So our range is going to go from -4 all the way to infinity, or you can write it as y is greater than or equal to -4. Now, our domain of our g inverse of x, well, we always read domain from left to right, and our first x value that is touched is right here at x equals -4. So I'm going to say that it's going from -4, and then we have an arrow pointing to the right, so it's going from -4 to infinity, or all x values is greater than or equal to -4. For my range, I always read from bottom to top, and my first y value that is touched is right here at 0. So it's at 0, and then I technically have an arrow that's pointing up. So my range is from 0 to infinity, or y is greater than or equal to 0. And what we can see here is that the domain of our original function becomes the range of our inverse, and the range of our original function becomes the domain of our inverse. They end up flip-flopping each other. And so that is something that I want you to always keep in mind, is that not only do the x's and the y's flip-flop, the domains and the ranges also do as well, as we see here in this picture. Let's go ahead and look at a cubic function. So in example number 2, we have considered the function h of x is equal to 8 times x cubed. And we want to find h inverse of x. So I am going to write down our original function of h of x is equal to 8x cubed. I am going to replace h of x with y, so y equals 8x cubed, and then I'm going to switch x and y, x equals 8y cubed, and I know at this step I need to solve for y. So I'm going to start by dividing both sides by 8 first. I end up with x divided by 8 is equal to y cubed. And just like we did in our warm-up, we're going to take the cube root of both sides. The cube root and the cubic exponent are going to eliminate, leaving us with y. And now from here, I'm going to take the cube root of my numerator and divide it by the cube root of my denominator. This ends up equaling the cube root of x divided by the cube root of 8, which is 2, equals y. To clean it up, I'm going to rewrite this as 1/2 times the cube root of x is equal to y, of h inverse of x. And so this ends up being what my inverse is. And now what we want to do is we want to graph both of our functions. So I'm going to start with making a table. Now, because this is cube root, and I know I'm allowed to take the cube root of positive numbers as well as negative numbers, I'm just going to let x equal -2, -1, 0, 1, and 2. And so I'm going to plug -2 up here. I know -2 times itself 3 times is -8. -8 times 8 is -64. -1 to the third power is -1. 8 times -1 is -8. 0 cubed is 0, and 8 times 0 is 0. 1 to the third power is 1. 8 times 1 is 8. 2 to the third power is 8, and 8 times 8 is 64. Let's go ahead and plot these points to the best of our ability. This is h of x. So this is a cubic function, so we know that it's a stretched out s. So clearly I cannot plot -2, -64, but I can plot -1, -8. Here is 0, 0, and here is 1, 8. And I'm going to connect these points, and I'm just going to draw like an arrow going straight down, and this is supposed to kind of look curvy, even though it's kind of hard to see that. But this is a very stretched out cubic function. Let's go ahead and look at our inverse. So our inverse function, that is where we flip-flop our x and y values. So I'm going to write -64, -2, -8, -1, still 0, 0, 8, 1, and 64, 2. And let's go ahead and plot these points. So I clearly can't plot -64, -2, but I can plot -8, -1, still 0, 0, and 8, 1. And what we see here is that this is going to be a reflection across the line. Y is equal to x, but it's a very stretched out, long S kind of shape. And once again, what we see here is that it is indeed a reflection. These two graphs are a reflection across the line. Y is equal to x. They are graphically inverses of each other as well as algebraically inverses of each other. They are reflections across that line. Y is equal to x. So let's go ahead and look at our domain and range. Our domain of h of x has an arrow pointing to the right. Technically, all the way down here is going to the right. And we technically have an arrow that is pointing to, we have an arrow pointing to the left and an arrow that's pointing to the right, indicating that our domain is going to be all real numbers. You can use the all real number symbol, or you can write it in interval notation. Our range, we have an arrow pointing down and an arrow that's pointing up, so our range has no restriction. It's going from -infinity to +infinity, or simply all real numbers. And the same thing is true right here for our inverse function. Our inverse function, we have an arrow pointing to the left and an arrow pointing to the right, indicating that our domain is going to be all real numbers. And our range, technically this is an arrow pointing down, and technically this is an arrow pointing up. So our range has no restriction. It's going from -infinity to +infinity, or you can write it using the all real number symbol. So what's cool about cube root as well as cubic functions is that there is no restriction on the domain. And it's harder to tell, but we did flip-flop the domain and range values. It's just that they remained constant. So to recap and summarize what we've learned today, this is a summary of square root and cubic functions that will lead into our next lesson. A square root function, or a function that has a power of 1/2, has a parent function of the square root of x, or x to the 1/2 power. Its domain is restricted. Its graph is going to be a graph that has a starting point. So that starting point could be anywhere, but it will have a starting point. And that starting point, kind of giving you a hint as to where we're heading, is going to be your h and k values. If we were to talk about the function in the form of y equals a times the square root of x minus h plus k, that's kind of giving you a clue as to where we're heading. Our domain for any sort of transformed graph is going to be h to infinity. And our range is going to be based off of our k value. And we will talk about that in our next lesson. Our parent function domain is going to go from 0 all the way to infinity. And we will talk about the range, like I said, in the next time that we see each other. For our cube root function, a cube root function looks something like this. It's a stretched out S-looking shape. We would write the cube root function as the cube root of x, or you might see it as x to the 1/3 power. The domain is not restricted. It's always going to be all real numbers. So regardless of if we have the function y is equal to a times the cube root of x minus h plus k, your domain is always going to be all real numbers. So there is never going to be a restriction on the domain for cube root functions. That is the end of today's lesson. If you have any questions over anything, please feel free to reach out to me. Otherwise, I hope you have a wonderful day.